Laura. So yesterday I presented you a microscopic model for crowd motion based on a granular principle. I would like now to present you a macroscopic version of that. And actually the most interesting, I think, would be to compare to see how far away both models are. This is a very particular situation where clearly macro approach cannot be performed in a proper way, and actually I will try to show you that the microscopic model is much richer in this context than the macroscopic one. So the situation that we can have in mind is, again, evacuation of a room. Yesterday we had, and you saw with Sylvain, a bunch of people trying to get out. I will present you some simulation of situation like that. And now we replace that by a continuum rho of x and t. And we would like to write basically the same model at a macroscopic level to try to analyze it. And of course, as you can expect, there also will be a Laplace operator that will emerge. And what we'll do afterwards is try to compare both the discrete and continuous Laplace operators and see that they are very different in this context. So the model writes very easily, actually. You are given desired velocity field, basically corresponds to the shortest path to the exit. So you are given u of x and t. That is given is the desired velocity field. And you say that u will be the actual velocity. And you simply transport rho in a conservative way. You don't want to lose mass, of course, by the, no, not the desired velocity. If you do that, then it will obviously lead to a violation of the constraint, which I did not do, right? I want my density, say L1 of R of R2, I want the density to be non-negative, to be less than 1. Of course, it's non-negative, it's the density, to be less than 1, sorry. So 1 is my maximal density. In practice, that would be about 6 or 7 people per square meter. I fix it to 1. So I want to remain in K, but of course, if the field is concentrating, I will violate the constraint. So this should not happen. So I have an actual velocity that is defined as previously as a projection of the desired velocity on something that is a set of feasible velocity, which I'm going to write. So it's a set of velocity which are compatible with the constraint. I will of course express it. So it's very simple, and as you will see, I have to say that I wrote this model perhaps 12 years ago. It took me perhaps 3 years to have the first hint how to handle it. I mean, in a theoretical way. I will show you. It's not so simple. And then it took us with Filippo Santambrogio about 2 years to finalize it. It looks at least very simple. It expresses very simple principle. And let me just say that this is basically common work with Filippo Santambrogio and also Aude Roudneff-Chupin, who was taking her PhD at that time. Okay, so the set of feasible velocity, what it means? It means when you have the density that is saturated at 1, you do not want to get higher. So basically, in an informal way, is the set of velocities. You will see that the natural regularity is L2, but it's not very important here. L2 of some set omega, so it's a vector field, such that informally, when you have, you have the divergence of V that should be non-negative wherever rho equals 1. Because if it's negative, it will increase rho, and that is forbidden. Okay? So this is not a proper definition, but it can be defined more properly, and that will be important for the following. In the following way. So it's still a bit informal. You want the divergence to be, I will say it with inequality, minus the divergence to be non-positive on rho equals 1. And this is still a bit informal because the velocity is simply L2, so the divergence is not properly defined, but you can just write it in a dual way. So this is okay. This is a proper definition, L2. You use test function, and I call them P, and you will understand why. It's such that V dot gradient of P is less than 0 for any, you see I write it, I multiply by a test function, I integrate by part, and I have the derivative carried by the test function that is regular. So I take a function such that the gradient is in L2, that is called, even if you're not too familiar, it's called the Sobolev space H1. And I want Q to be non-negative because I express in inequality constraint, and this field will be the field that you feel when you are in the metro, that you are compressed by people. This is pressure, you are always compressed and not pulled apart. So the fact that it is positive, it really means that. It's some kind of force field or pressure field, like in an Euler fluid, for example. And so for all, and I also want the constraint to act only when the constraint is saturated. If here I am not supposed to feel pressure from you because you are far away. So there is no pressure. It has to be forbidden. The pressure should not act when people are far away or when the constraint is not satisfied, is not saturated. So I will prescribe Q times 1 minus rho equals 0. This forces Q to be 0 whenever rho is strictly less than 1. Okay? So that forces the Lagrange multiplier to act only when the constraint is saturated. And this is properly, you can show that this makes sense. It defines proper Hilbert space. Well, the problem is well defined. And this is actually an intersection of half space. So it is actually a closed convex cone. So at least this projection is well defined. Perhaps not too easy to compute. But so what is complicated? This step, because you project on something that is very Catholic set, like everything is okay, closed convex cone, etc. And what's the problem? The problem, well, the difficulty lies in the fact that this is very irregular. The dependence, typically it has the form dt rho plus divergence of a flux function f of rho, where the dependence rho f of rho is given by this projection. So U does not depend on rho, but this set depends on rho. So what will happen? Happens at sometimes you have no constraint, and then suddenly, like in the microscopic setting, you have a saturated zone, and they can be very, very complicated. And actually, one of the difficulties we met is it's difficult to exclude a priori the fact that the saturated zone, this, might be very complicated. For example, we had some problem with the, you can imagine that you have a population described in a macroscopic way by something that is the complementary of a dense open subset. You see, I don't know if you know this kind of counter example, but they are awful to write properly thing. You consider you enumerate a dense subset in, for example, this square, okay, and you put small balls with decreasing radii in such a way that the total measure of those balls is very small, the complementary is your saturated zone. So you have some kind of bizarre, some kind of bubbly material where the saturated zone has almost full measure if the circles are very small, but it has empty interior. So there is no place. It's like if you are in a very, very dense crowd, in a macroscopic crowd, and you always are in contact basically with some empty space, but still it's very, very dense, almost full measure. So let me forget that. It was just to mention that it's a bit difficult, even if the definition is clear, it's difficult to figure out what is rho actually, and there is no regularization process for rho, and so that is very difficult to be sure that that will not happen during the process. So let me get back to that. So this is very irregular because the dependency is very non-smooth in time like before, so we are with respect to rho. So we are far away from using standard tools in PDs. So what could be, yeah?
And this function f of rho is not local.
It's not local. You are right.
Rho of x and t, right?
Yeah, you are right. It's a functional function. It's not local. It's not f of rho of x, because, and we will see that there is non-local effect because of this kind of incompressibility of the fluid. You are right. Okay, yeah, so what could be done? I will explain in a few minutes what took me actually a few years at some time. What could be done for that? You would like to, it's tempting to try to implement what we did in the microscopic context. Microscopic, let me rewrite you the problem. So you have dq over dt, that is u, and this is actually the Lagrangian version of this transport equation, which is a real equation, and here is some kind of tautology, but since the model is Lagrangian, we just say that derivative of the position is the velocity. And we had u equals the projection and cq of capital U. And what is important that we had, if you remember, there was some kind of algorithm that was like that. So k was the set of position without overlapping. So all the dij's of Q were non-negative. And we had a prediction correction scheme. At each time you take the position, you move them, tau is the time step, with respect to the desired velocity. They don't care about each other, so they violate the constraints. You get something that is not feasible, and you project it onto the set of feasible sets. So that was the projection of K on that. I will come back to this projection because it's not so well defined, because K is not convex, but it's not too far from being. I will come back to that because there will be also a huge difference between micro and macro in this highly packed situation. So that was the so-called catching up algorithm proposed by Maury for the sweeping process, but it's commonly used in scientific computing, for example, to solve Navier-Stokes equation. Okay, so could we do the same? So here this equation is simply, you write it, and we had this projection over 0 of u, and then it would be tempting to replace that by having a predicted density. So what is the transport with the unconstrained velocity? It has to be replaced by a transport by u, and what is written the most natural way. So you might solve the transport equation during the time step tau with the desired velocity, forgetting about the constraint. But there is another way to do that that is simpler. You consider the identity plus tau uk. So this is a displacement field. You take the let me consider that this is constant, which is the case. You apply the displacement for each x, put x plus tau u at x. You move the point. So you are at some place. You have an application, a mapping, and you take the image measure of k with this application, meaning that you move with the desired velocity. So what will happen in this situation if you have a field that has a negative divergence that is concentrating, you will surely, if it was the density was 1, you will violate the constraint. So this is not feasible. So if it's not feasible, we just project it on k plus equals to a projection of k, rho tilde k plus 1, sorry. Okay, so this is formally the equivalent you do in macroscopic, what you did in micro. So what's the problem? In which sense are we going to make this projection? We deal with densities. We can see them as function. So there are many ways you can take any norm, and I will show you that you have to be very careful in which way you do that. When we project here, it's based on Euclidean norm of the Lagrange. If I have two configurations, this one goes here. The difference between those two is just this distance squared, this distance squared, this distance squared. Okay, and you take the square root. So you have, if you have a displacement, it's considered like a Lagrangian displacement, where here, if you are naive, like you consider, for example, in 1D, you have a density that violates the constraints. So this is a density, this is 1. This is like some kind of row tilde, it violates. I want to project it onto K, the set of densities that do not violate the constraint, that are below 1. If you consider, this sounds like L2 norm, so why not use a L2 norm here? I guess you know that when you L2 project a function, you just cut off. It's very simple to perform. You just separate this. Okay? So the problem that will give you a model such that when people go to the exit, if there is congestion, then you will lose people. They will just disappear. So of course it will work fine to evacuate your room, but it's not, you see, very well acceptable from I don't know, humanistic point of view. So you might say, okay, I don't want to lose mass, so I forbid to lose mass. I am projecting onto the set of functions such that the mass is 1, the total mass is 1. But it's still completely absurd if you consider this 1D situation. So here I violate the constraint, and I want to project onto the function here in the L2 sense such that the density is below 1. Or in the L2 sense, it will take this mass and put it here as small as possible. It's the principle of least square principle. You just spread mass. So that will lead to a model such that when people go to the exit, when you have congestion, then you have all the people that comes back to the room, and you see what I mean. It's completely, it does not make sense. So the problem is that, can we find a way to project a good distance on the measures which in some way respects this Lagrangian character of molecules? And there is one. I didn't know at that time, I have to say. But there is something that exists since a few centuries, but which was came back about 3 or 4 decades ago. It's the optimal transportation. I don't know if you are familiar with that, so I'll say a few words about that. When you have two densities in RD, so here I consider measure. Let's say probability, the important thing is that they have the same mass, say 1, but it's not important. Using the same notation, I can consider mapping R2 to RD, and I will I will write that T sharp mu equals nu. Simply is nu is the image measure of mu. Nu is the image measure of mu by T. Okay, so which, for example, means that nu of A, some new measurable set, is equal to mu of the reciprocal image of A. Okay, you just transport mass, and then if you are given a cost C of x and t, C of x and y, sorry. So it's just a function defined on the product. In my case, that will be some function of the distance, but that can be anything, actually, with some regularity assumption. You have a cost, corresponds to the cost to transport a unit mass from x to y. And you have, when you have a transport map, you can estimate its cost by writing C of t equal, you integrate C of t of x, x d mu of x. So this gives you, when you transpose x to C of t with transpose little pieces of mass, you get a total cost, and you want to minimize that. And this is the optimal transportation problem. Minimize the optimal transportation problem among maps which forward push mu to nu. That is the expression that is used in general. Okay, so this is the problem, the basis of optimal transportation. Okay, so how can it be used here? If you consider quadratic cost Cx and y equal to x minus y squared, you can define what is called mu and nu. That is, by definition, I said a minimum because at least under some assumption it is actually reached of x minus y, sorry, t of x minus x integrated against the measure such that integral of mu. So you define this quantity as the minimizer of this problem. And given you have some assumption on the mu, it can be shown that there is a solution to this problem that was a minimum. Actually, it exists. It's typically, well, for the quadratic cost, they have Brenier, who is a colleague at Orsay, actually, Brenier's theorem. I think it was about 30 years ago now. Okay, and what is interesting is that you can define this quantity W2. W for Wasserstein is called the Wasserstein distance. You can show that it is actually a distance. It separates things. It's obviously symmetric. Well, it's obviously symmetric. It's not so clear because in some situations, let me just say that if you have, for example, a Dirac mass and a diffuse measure, you can transport the diffuse measure onto the Dirac mass, but you cannot transport with a transport map the Dirac mass onto the diffuse measure. So under some assumption, it can be shown, for example, like the measures are all diffuse. They do not contain atoms. Then you have symmetry, and you also can show that you have triangular inequality. So this is actually a distance that can be used. And this is the right way to project. So this will be the projection with respect to the Wasserstein distance. And let me just illustrate how it works when you have this situation. Basically, when you try to solve this projection problem, it will try to find some velocity field or displacement field. It will take the matter. So the idea that you have in mind is not that you take this mass and you put it here. It's more like you deform the whole set by having those points move, and you try to look for the cheapest, in this sense, the cheapest deformation that brings this mass distribution onto something that verifies the constraint that in that case will look like that. Okay? It's a very powerful tool. I guess most of you know, but I realize that some people do not that so much. It really changes the vision you can have of many problems. Let me, for example, when you have two functions which represent measures here, I have two Gaussian, but the usual way to measure the difference between both is a Eulerian one. It is the PDEs, partial differential equation, are really based on the Eulerian version, meaning you look at some point and you see what is the difference of the function. So if you consider L1, for example, L1 norm of say f minus g, it's the area of this that is represented here, okay? And now we have another more horizontal way to measure variations and things. It's horizontal. You see, you are trying to move this one to that one. So you try to find something and you try to see in a horizontal way. And it really makes a huge difference. For example, what I like is, it's not related to crowd motion, but for example, a Eulerian distance will make no difference between those two situations, 1 and 2 and 1 and 2. If you take you integrate the absolute value, that makes the same positive value. Yeah. Whereas with optimal transportation, you rarely get a measure of the transportation you have to perform to get from one to the other. So it can be very interesting also in image analysis, and it's used by to design proper loss function in a machine learning procedure, like for example Gabriel Perret uses optimal transportation, especially to design adapted loss functions. Okay. Yeah, so let me say one word about the project. You see that things are not so easy, and these remarks will make us realize that there is a deep difference between the microscopic and the macroscopic model. Is this projection well defined? We will see, I will not show it, it's not so easy, but it's not very complicated, that there is a unique density, that this problem is well posed. So this is not, you cannot use standard argument. Let me just say that you might say that, okay, you project onto a closed convex cone. That is not, we project on a set, but this is not a Hilbert space. You are in the set of probability measures. There is no Hilbertian structure. It's not even a linear space. So it has to be properly defined, this projection, and we cannot use the Hilbert projection theorem. But it can be shown that it is actually well posed, and I would like to show you that it is in some way paradoxical. Let me get back to the microscopic situation. We had this scheme can be written Q equals PQ of Q tilde. We have some Q tilde that violates the constraint. We project it. So the typical situation is this one. And you project, and you will separate apart in a cheap way, the cheapest way, the particles, and you get that. But if you have two particles that highly violate the constraints, so you take for that and you put them at the same place. So now you want to project on K. Of course, there are many ways, infinitely many ways to project on K if you want to, those not to violate the constraint. You can have the situation you came from, but you can have any other one. You see, those realize the distance from this configuration to K, okay? So, and that appears in the scheme if you want to represent K in this way, which I did yesterday. So, since this is not convex, you can have in some, if you go too far away from the boundary, you can have multiple projection, okay? So, and what happens, what you can check is that if you have many, many particles, more and more particles and smaller particles, it degenerates. What do I mean is that if you consider the set K, and if you consider the largest eta neighborhood, such that the projection on K is well defined, obviously when particle gets smaller, it degenerates, meaning you cannot go far away from the set in order to get a proper projection. I don't know if it's clear that it really degenerates when eta goes to 0. What I'm saying is that even the algorithm, the basic algorithm, it obviously tends to degenerate when you have the number of particles go to infinity and their size go to 0, which is of course a problem if you want to establish macro results. And so it also suggests that since it degenerates in the many particle situation, you can expect a very bad behavior for the macroscopic one, okay, like a catastrophe. That is not what happens, and I will explain you why. It took also me some. You will see that it's very simple, but it took me some time to realize it. When you have the situation, let me consider a 1D situation. So this is a ball, disk, and I have the critical situation, like the two at the same place. What we saw in this case, there are two projections possible. This one, so you can either recover what we came from or flip it. So you have an undetermination. The projection is not well defined. What is the macroscopic version of that? You have a saturated zone, and then you bring them together. So here you have density 1. Here you have density 2, and then you project. But you can see that there is only one way to project. That is this, and since the macroscopic forgets about the labels. Okay, this is not purely Lagrangian. That is what is tricky to understand, is that optimal transportation seems to reproduce the Lagrangian description of matter, but is Lagrangian up to a permutation. And it's very important that when you when you represent a density, you do not follow labels. So this, for the macroscopic set, from the macroscopic point of view, this is equal to this, because there is no difference between blue and white. There is no memory on labels. And just last remark to insist on that, if you consider atomic measures with n, like some objects which were considered in previous lectures, like you considered n points, and you considered measures of mass, total mass m, which have that form. Okay, was actually they might be at the same place, not problem. Then the mass will be 2. But okay, so you have a set of measure, and you can define the Wasserstein distance within this space. So this is called discrete optimal transport. And in that case, it pretty much looks like the Euclidean version. You will estimate ways to, it's a pairing, it's really the discrete version of that. And actually, it amounts to minimize the sum of y phi of I minus xi. And you are looking for the permutation. Here you have some numeration, 1, 2, 3, and 1, 2, 3. So you want to have 1 go to 2, 2 to 1, and 3 to 3. So you're looking for right permutation, okay? And it takes this simpler form, and this gives you the Wasserstein distance. But it pretty much looks like the set R D to the n, the set which corresponds to the microscopic version, where you have collection of endpoints embedded with the Euclidean distance. Do you see the difference both? You might see that as metric spaces, they are identical because they represent the same thing. But there is a huge difference because here you have labels. You have 1, 2, 3. And the vector 0, 1 is not the vector 0, 1, 0. It's not the same. And here is defined up to permutation. So you actually have an identity in terms of metric space that is an that is isomorphic in a metric way. So there is an isometry between an and this. But you see what something is lacking here. It's not an isometry. You have to take the quotient with the permutation, say that. You can get a metric space. So this is real. And this is important. This is just a remark, but it's important to understand optimal transportation. When things do not move, usually it's not too bad. You have particles. They move a bit if you want to model evolution problems. You have small motion. And when you have two densities, two atomic measures which are not too far away from each other, then there is a natural mapping. But as soon as things move significantly, then you lose track of things. And that is actually something that causes problems. Sylvain told you yesterday about what we do to measure people. That's a problem if you want to follow people in a crowd. You want to count people. You have images, so you have points, you have dots. You don't want to take pictures because it's forbidden by the law, so you want to have dots, and you have an image and then another image. If the two images are taken at there is a very short time between both, you can do matching and you can use optimal transportation. But if you wait too long, then you are lost because you do not know how to match. So that's one of the difficulty of velocimetry when you want to measure velocities, just using snapshots of indistinguishable particles. Okay, let's check the time. So I started at...
Yeah, 50 minutes. You have still 50 minutes.
50 minutes, okay, that's fine.
Before
yeah, okay, that's fine. So now I would like to talk about, we heard about gradient flow in the different contexts in the first lecture. I would like to come back to the gradient flow structure. I think it's enlightening, and it's actually what makes it possible to get theoretical theorems, even if I'm not going to go into details in that matter. we are in a metric space. So of course there is a huge theory, but actually I hope that you agree with me that the principles are not so difficult to understand. We just measure, when you have two measures, you want to transport the first one to the second one with a displacement field. You estimate the norm in a standard way in the displacement field, and you find some, you try to find some minimal way to do that, and it gives you a distance. So it gives you a space, which I will call the space of probability measures with this Wasserstein distance, or the mass could be anything, but it could be different from 1. And you can write gradient flows on that, which is not so easy a priori, because the set of probability measure, of course, it's not a Hilbert space, and there is no differential structure a priori. You keep in mind that you can have very non-smooth things in probability. You can have atomic measures, etc. So the notion of gradient is not so easy to grasp, but something was proposed a long time ago at a very simple and very fruitful idea, which I'm going to, I think it was the Georgi, I'm not sure it was even published, but it's like an idea to generalize the notion of gradient flow. So the idea is the following. If you consider a straight gradient flow minus the gradient of psi, where psi is a smooth function in a Hilbert space, so you can define the notion of gradient. You can discretize it in, for those who might have done some numerical analysis or scientific courses. There is an algorithm that is quite common to solve that kind of problem. You have a time step tau, and you use a finite difference philosophy to discretize that. And there was two ways to do that, explicit or implicit. It depends on if you put k or k plus 1. If you put k, it's very easy to solve. It's explicit. Well, it's actually the case that you have, that you can make explicit computation. But here, if I put k plus 1, it might get more complicated in practice, because this might be a nonlinear problem. You might have to use a Newton method. It's difficult. But it's known to be more stable. Anyway, I'm not interested in numerics here, just theory. And you can check that this is optimality condition with respect for, say, for some functional that is phi depends on tau, phi of q is equal to phi of q, psi of q plus 1 over 2t q minus qk square. What I'm saying simply that if you take this functional, you take the gradient, okay, and you write that the gradient is 0, then you get exactly that by changing the place of thing. What it means is that if this function has good properties, and it's quite general. For example, even if psi is not convex itself, but you see that it will convexify things. So if psi is smooth, let's say that his Hessian, for example, is bounded from below by some fixed matrix, or the identity times a negative constant, then I will recover a convex function if tau is small enough. So this is typically a convex function, strictly convex function. Also, it's coercive. It goes to infinity when q in norm goes to infinity. So it generally has a minimum, and it is unique. So under a quite general assumption, this scheme can be written q minimizes psi tau of q. Okay? Because qk plus 1. Basically, having that, because again, if you have a convex function, then vanishing the gradient corresponds to being a minimizer. So it's really, it ends up to minimize this function. So let me write it like that. Spare some times. Qk plus 1 in the set of minimizers of this function. Okay, so this gives you another way to write the implicit RX scheme, and there is no gradient here. And what the trick is simply if you are in a metric space with some general metric, with no linear structure, you can just replace that by d of q and q tilde to qk. Okay, so what is, it's not finished completely, but imagine you are in a metric space, quite general metric space, and q is some point of this in this metric space. If you handle with a function as such that such a function typically emits minimizer, what is important is not to have uniqueness. You might consider this pseudo algorithm without uniqueness, but you need existence. But in quite general situation, you will have existence of a minimizer. It gives you a theoretical algorithm to compute discrete solution, qk plus 1. And you can have tau. They all depends on tau, of course. And you can have tau go to 0. Then you have a set of discrete solution. And you might expect that possibly up to extracting a subsequence, they might converge to something. If it's the case, you will say that this limit is, in some sense, a gradient flow of your functional psi. So it's very powerful. It can be used to define gradient flows when you do not have gradients. And actually, it's not called a gradient flow, but a minimizing movement, or there are many equivalent or almost equivalent ways to describe that. But it's really something like it's the steepest descent motion, if you wish. So for crowds, the macroscopic, it can be directly implemented. You can write, and this is actually the first, with Filippo Sant'Ambrogio, the first result that we had to establish this problem. We directly write, so it's not exactly the same philosophy. Here it was a prediction correction algorithm, and here when the velocity field is the gradient of functional, we can use this gradient flow setting by solving everything at the same time. And u rho k plus 1 is in minimize, or what is the dissatisfaction function that people want to minimize? If you remember well, in the microscopic situation, it was the sum of distances, okay? And here it's simply the integral of the distance with respect to the measure. So people want to minimize that to be close to the door. And then you add the indicatrix function of the constraint. This is plus infinity if the constraint is violated. In that case, you will prevent your system from violating the constraint. And then you have this inertial term so that the next solution will in some way stick to the first one in order to get a continuous evolution. That is 1, 2. And here I have the distance, which I take the Wasserstein distance, rho k and rho squared. Okay? So this is simple to write. And what is a bit tricky and is to, from that, to characterize minimizer for this and to see that you actually obtain the problem you wanted at the beginning. So that's the technical part. But the philosophy is quite simple. And this is very general. And let me perhaps tell you, if I have a few minutes, I would like to say a few things on this, because this is very rich. Not only it was not created clearly for crowd motion, we used it, but this comes back to the, I would say, there is a paper in 98, I would say, 1998, by Kinder, Lehrer, Otto, and J. Jordan, Kinder, Lehrer, Otto, to interpret the gradient flow of some very special functional, which I would like to talk about. But let me first make a few remarks on the work that we are currently doing. Sorry, that's some kind of it's a bit removed from gradient flow, but it's a work in the same philosophy, something we are interested in. I would like to give you examples of function that could be interesting to minimize with respect to measure and to consider the gradient flow associated with. So this is just a remark. It's related to work that we have in geography with a colleague that is a geographer. The problem is the following. You want to find interesting problems in terms of, you want to minimize measure. The idea that you have some land, typically in the prehistorical space, you have people coming like in the far west in the States, or a bunch of people arrive, and then how can you explain that 10 years or 1 century later, you have people there, you have a town here. How can you model this settling phase? Well, and you see the population as a measure that tends to minimize, of course, or maximize if you wish, but that will minimize things, minimize some kind of dissatisfaction. How can you model that? And that's interesting too, and this framework is very well adapted to that. So you want to have a problem that consists, so rho is a probability measure, but on say R2 if you are in a country, in a flat country. Probability or any mass, of course the mass is not important, and you want to find an interesting functionality that you would like to minimize. So the first thing, if you have like a landscape, for example here, when I think there are some trace of prehistorical people living here, it was I think a nice place with perhaps the river was a bit different, but you can imagine in 1D that you have a landscape. So this is something I will call J, which depends on the space, under the convention that is interesting when it's low. You want to minimize this. Basically, it means that here you have a very nice place. You have access to water, but it's not too wet, perhaps, and you have trees. You can okay. So this is interesting. This is less interesting, and this is not very interesting. So the first problem, the simplest one, is the problem which consists in minimizing integral of g of x, so it's a linear function, against the probability. So it's not very interesting, of course. Here you will have a Dirac mass here, or possibly split it if you have non-uniqueness of the minimizer. You might split your measure in different. And let me say that you can consider the gradient flow of this functional, and this is not very rich, but what will happen if you consider the gradient flow in the Wasserstein space associated to this functional, it will give you simply like infinitely many ODEs in parallel associated to like rho. The rho that the initial measure that you have would be a measure over the set of initial condition for your Cauchy problem, and you will find something like that, an evolution, a transport equation, where u is simply minus the gradient of g. So it's not just a nice way to write infinitely many gradient flows. When I say the gradient flow, the individual gradient flow is dq over dt equals minus gradient jq. That would be the microscopic version. Okay, so you can add things. This is not very realistic, because there is not enough space. You have 1 million people. They cannot all be at the same place. So you will add something to model the reluctance of people to be too many at the same place. For example, so you have this, and you can have a term, for example, the power of rho. And you can even have m go to infinity. That's interesting. It's difficult, but interesting, just to penalize the fact that being more than one. So it will handle promiscuity, the fact that you don't want to be too many at the same place. But actually, most models are based on that in the mathematical literature. They are based on the vision that people, they just want to optimize their own utility, and they don't like other. They want to be alone, cool, etc. But when we discuss with geographers, they insist on the fact that what makes cities, that people know they do not want to be alone. They want to be with others. Of course, there is a practical interest in that, but they also want to be gathered, not too much. So you can imagine, for example, to add another functional that is, for example, the distance. If you integrate this for x is the average distance from x to the neighbors, and if you double integrate it in rho of x dx, you have something that measures the dispersal of individuals, and actually it's natural to consider they would like to minimize this, okay, because people want to be together, and that's what we are currently going to do to see to investigate the property of this minimizer, and to consider the gradient flows associated with that. So in some sense, this is a very simple situation. The crowd motion is a very particular situation. It's dynamic, but the functional that we minimize is of this time. It's very simple. The difficulty comes from the constraint, as I told you. So, okay, so let me just say some words about the Laplacian, come back to the Laplacian. I will not come back to convex analysis, which I did yesterday. Just you will see some picture that will remind you what we did. And I'm quite aware that this might not have been very pleasant for some of you because it's a bit technical, but I hope that you have understood that it makes it possible to understand interesting, I hope, things in terms of behavior of highly crowded motions. So let me get back to the, again, the question, where is the Laplacian? And I'm saying, this problem, I don't know if you see a Laplacian here, I don't, but there is one. Actually, it's hidden, again, like in the macroscopic situation. There is no diffusion in the model. There is nothing that reminds of the Laplacian, but there is one. And we'll see. If you remember the picture we did yesterday, I will just redo it rapidly. Here we had CQ was the set of velocity such that basically Eij dot Vi minus Vj negative, meaning that when particles touch, they do not want to touch more if you want to overlap. So this was this cone, and we say that it was the reciprocal of the polar cone of some closed convex cone. And the interesting point was that the polar cone of this was B star of this cone. So if you remember well. Actually, I will not come back to this theory, but we have the same in infinite dimensional setting. The only difference is that lambda plus, let me write, is the set of Lagrange multiply, the set of pressures in H1 such that Q is non-negative. So this is actually a closed convex cone. Okay? This is actually, the picture is not very legitimate because this space is not identified to its dual, for those who are familiar with that. So in some way, those two cones, they are mutually polar, but they live in different, this really lives in the dual space. But this is a detail. And what is what plays the role of the matrix B that expresses this constraint? It's simpler, actually. B is an application that takes a velocity field and computes its divergence or minus its divergence. Let me put it under quote because it's not properly defined for L2 function. So it's the divergence, let me write it, defined in a dual way. If you take Q test function, which such that its gradient is in L2, this is defined by V dot gradient Q. So, but basically, if for regular function, it's really the divergence. And we want the divergence to be non-negative, okay? And so this is this operator, and I will not go into detail. Let me just tell you that even in the infinite dimensional space, we have the fact that the polar cone to 0, this is equal to B star of lambda plus. That's not so obvious because this what is easy to prove is that you have the closure of this cone is here, and you have to prove that this is closed. But it's not so difficult for those who are familiar with that. If you have already, for example, dealt with Darcy problem, it's exactly the same theory, or it's even useful in also in Stokes or Navier-Stokes equation. The important fact is that this mapping from L2 to the dual space of H1 is surjective, is onto, and its agent is one-to-one, and that makes everything work fine. So what is the consequence of that? So let me remind you that for the microscopic situation yesterday, we had B star, P equals BU, which I will interpret like a Poisson problem. And for the macroscopic situation, we have what plays the role of that. B is minus the divergence, B star is the gradient, so you have minus the divergence, the gradient P, equals to minus the divergence of U. Okay, so here we have a proper Poisson problem in the macroscopic situation. So we have our Laplace operator, and what I would like to say now is that I will show that the macroscopic model is a catastrophe in terms of modeling, because it does not even reproduce the capacity drop phenomenon, and that can be shown. It's a negative result, but it can be proven. And now I will try to, I will say a few words about the fact that this has very bad properties, this BB star. It obviously looks like a Laplace operator. It's really, there is a dictionary between both, but we'll see that in practice it's not, it's bizarre operator. It does not verify the maximum principle, and that's what explains in some way that you have problems when you have many people upstream a door. So let me first do that, and that's why even for those who know functional analysis, that could be quite easy, but it's not based on very sophisticated argument. When you have a crowd, rho equals 1, trying to escape a room, here you have an exit, so I will consider that the pressure is 0, meaning that it's very easy to leave. Here, I cannot go across walls, so the right position is that you want to say that u dot n equals 0. And since the desired velocity is here, that will give you a Neumann boundary condition, dp of n equals 0. And here you also have, there is nobody here, or you have no congestion, p equals 0. So you end up with a Laplace problem, a Poisson problem. Here you have minus gradient p equals minus divergence u. The u is concentrating, so the divergence is negative, so minus the divergence is positive. So you have this problem in a domain with a homogeneous boundary condition, Dirichlet and Neumann also. So it's exactly as if you were heating a plate with this form, and here you prescribe a 0 temperature, here 0 temperature, and here no impervious condition, no flux condition. Obviously, anyone, 4-year-old children would say that the temperature is positive inside, and that's what tells you that the maximum principle will allows you to say that in a proper way. But so the pressure is positive inside the domain because everything is positive basically, and the consequence is that when you are on boundary, your velocity is equal to u minus gradient p. So your normal velocity in the direction is u dot n, capital U dot n, the desired velocity, minus gradient p dot n. So this is minus dp over dn, okay? But since the pressure is 0 here and it's positive inside, dp over dn is obviously negative. So this is positive, so it tells you that people always go faster than what they would if they were alone. So this is the exact opposite of what you see in practice. When you have people upstream a door, they prevent each other from going fast. So you see that you have this capacity drop effect. I will show you some animation, but before I do that, perhaps let me say a few words on why in the macroscopic situation we do not have the same. What I told you yesterday was that in 1D everything worked fine, meaning that in 1D, when you have people in a corridor, the situation is not very rich. The matrix B is 1, minus 1, etc. 1, minus 1. You just express constraints here. You just say that this has to go, if the touch has, the velocity has to be larger than that one. And you do that for all contacts. So the number of rows of B will be the number of contacts. So the number of particles minus 1. So this is slightly rectangular. And you have a B star that you can imagine, so B transpose. And as I told you, B star is the Laplace operator, discrete Laplace operator. So it really looks fine. You say, okay, everything works like in the macroscopic setting. But as soon as you are in 2D, and of course 2D is the interesting situation, or even 3D, of course, if you consider granular material. In 2D, what happens if you have a congested situation like that? The first idea important is that there is a simple graph associated to that. There's something we use in computation. This is the primal graph. You just related the center of vertices. So this is a graph, a planar by construction graph. You can put a Laplacian on it. If you had diffusion between compartments, that would express some kind of heat equation. That works fine. But here you see that the Laplace, the gradient, it acts on pressures, and pressures are Lagrange multiplier, and they are defined on contact points. So the Laplace BB star, it does not act on this graph, but on the dual graph, the vertices of which are the edges of the first one. So, and this graph, you can draw it, and it's not so nice because first, so it, you know, it have points, contact points communicate when they share particles. So it has this shape, and I come from the finite element community. I have been doing a lot of computation for fluid mechanics on finite element meshes. I wouldn't like to do a computation on that kind of mesh. You see, there are triangles in any direction. This is really messy. And more dramatically, this does not verify. So I hope you will agree with me that at least there is some reason to call that a Laplace, some kind of Laplace operator, because in one it's exactly that. Formally, we obtained it exactly like this. But here, you can show that, for example, the interaction term between this point and this point is the dot product of those two unit vectors. Okay? So it's basically a -1 if you have unit vectors. So that will give you the -1s, and that's okay. The problem is here, you have this interacts with this one. Okay? And the dot product between the two is positive. So you have the matrix BB star, you can check that it indeed has positive elements, entries in the diagonal, as it should be. And you have some negative entries, out diagonal entries, but you also have positive ones. And that's very bad. That's quite a normal. It rules out the maximum principle. And let me just perhaps end with a remark on something, virtual experiment that you can do to understand what happens. Basically, when you have some kind of material, continuous material, and you push it from everywhere, what it tells you, well, any model you use for that, you will find a positive pressure. You have to resist to some compression. So the pressure is positive. And that's clearly what you get here by the maximum principle with this. What is the microscopic situation? And equivalent to that, it's very easy to conceive. For example, you have 4 coins that you put on the table like that, and you glue them together. You glue all the contact points. And then you compress this little system that way, here slightly, and here strongly. You see what happens? The pressure here is negative. It has to, because it pushes. So this violates the maximum principle. Also, the pressure field is a solution of a Laplace-like equation, but it does not work because it has these very bad properties. Of course, in practice, in crowd motion, what will happen, you cannot have negative pressure, but what will happen is that you have separation. And this is also a bit pathological. Okay, so let me get to some animation so that we might have some time for the question, I hope. Do I have to do something? Yeah, the light.
And the ball.
Là, c'est bon. Et les tableaux, c'est ça? Oui, oui. Oh, putain! Pardon, je me suis pris la tige là, sur le pied. C'est pas bien. Je ne sais pas si on pourra couper. Voilà, bon, je ne vais pas revenir. Sylvain vous a montré, pour ceux qui étaient là, des exemples. Là, c'était le modèle de Helbing sur la droite. Oh, sorry. Non, sorry. Sorry, for those who were yesterday, so this was Helbing's model and then the cellular automata, but I'll not come back to that. So let me get to the microscopic model. This is an example of computation that can be done with chromosim. And here you have the solution to the aconal equation. It's a nice example, I think. So it's the geodesic distance to the exit, which is on the left-hand side on the picture. So you can check that this is when you have, like if you are in a, well, it corresponds, each line corresponds to a set of points where the distance to the exit is the same. And you want to follow, if you are a single individual, you will want to follow the gradient flow with respect to this landscape. And so this is what you will get. And then if you put many people and that you implement the constraint, you will have something like that. So of course it's very different. And this is exactly the model, the very simple model in terms of modeling of human behavior, which I presented you. I have to say that we chose to put large people like he did yesterday to have interesting things, like to have these jams, which obviously do not happen so commonly in practice, but we wanted to have some exciting situation. But at least some of them will go out. You can also put some social force. Yeah.
It's gradient flow for each of them independently, and then there is just a constraint that they...
Yeah, this is exactly the problem that I presented with this projection on K. Also, but it gives, like you said for the other problem, it's very non-local. It creates non-local effects through like in Darcy or any incompressible fluid, you have non-local effect. Okay.
Here you have designed the different patterns in order that they exit the fastest possible.
No, not at all. This is we took that from Centre Pompidou. I think it was perhaps a temporary exhibition. It was something that we took from the internet, but something that exists that might not be optimized. And we just take the blueprint and then we run the computation.
And can you solve this problem, say if you have only a few walls to design the best possible?
We can come back to that. It's always, it's a natural question to try to optimize. It's difficult to set up a well-posed problem, well-posed in terms of modeling, not mathematics, but say what are the real constraints. Even if you ask an architect, most architects, they do not live with constraint, they live with art. And so they just want to make beautiful things. They don't like constraints, so it's difficult. The problem is not so easy to formalize. And but you might, for example, what we do is that we just have we do parametric study. For example, you take a room, the walls are given, and you want to put 10 meters wide exits, like 3 plus 7, and etc. And you have this constraint, and you want to optimize. This can be done by exploring. Of course, it's highly non-convex, but this can be done. But the problem to optimize globally, it's not. I do not have a simple problem to set, and there are so many constraints due to many actors implied in building such things. An example of some structure that it looks a bit more like statistical mechanics in terms of I have this, there is no structure in the model. The blue, they want to go to the right, and the red, they want to go to the left. And you will see that you have some structure, one-dimensional structure emerge, like you observe in Paris sidewalk. And that, I think that's interesting. And there is no behavior that explains that. It's just purely as if people were blind. They just walk, and then when they hit people, they are just pushed by them. It's purely. But you find this quite well structured. Of course, it's a bit nastier when you consider more dense flow, and that's closer what might happen. We talked yesterday about Lamech. Lamech, when you have problems, you have counter flows of people that go, and here you can check that you have very, very high pressures, because the pressures of people, they add up, and then they make, I told you perhaps yesterday, about 400 kilograms horizontal force within a crowd. That's, of course, you do not survive to such a situation. Okay, let me back to a bit more academic case, but this is a case. The computation was made a long time ago, but it's very simple, but this is the one I prefer. Actually, it's very expressive. So you have just a crowd getting out a room, and I have this flow, this gradient flow with this function with individual distances and this non-overlapping constraint, and there is nothing else here. And so you see what you see the Lagrange multipliers, that when you have a contacts, there is an edge, the width of which depends on the pressure, the positive pressure. So you see that there is a very complicated, there are very complicated shapes. And what happens also is it's very irregular. It can be shown to be in practice. What was surprising, that to be able to recover this stop-and-go waves, stop-and-go effects, without any adapted specific modeling. It's just the geometry that creates that. And what happens after some times, well, if the door is not too wide, is that you have a perfect jam of everything is blocked. Actually, the first time we got that, we discussed with some colleagues working on this, and say, okay, no, that's not normal, that must be a bug. And actually, we heard that sometimes it can be observed in practice, and what the colleagues were saying, it's just that the other model do not reproduce that. So we have a model that clearly makes that, and it's not so unrealistic. I would like to show you.
So this is really a trap forever, or?
Yeah, it's trapped. That's a good question. We can check that we can define some sort of Hessian. It's not smooth, so it's a bit tricky, but you can define some Hessian equivalent, and you can show that you are actually in a local minimum of this pseudo Hessian. So this is really, of course, if you put an atomic bomb, you will blow it out. But if you push a bit, it will not. If you put some nose, for example, it shouldn't break. Well, this is perhaps just to see the structure of these force arches. So those represent the pressure. So you see, it's almost is the problem with 2D. You have a crystal-like configuration. Even if we take slightly polydispersed situation, the radii are slightly different, but yet you keep something that is structured not very realistic. But at least you see that you have strong lines going at long range. That is very important. I will perhaps come back to the fact the question that is natural here is there a macroscopic model that reproduces the microscopic situation? And that kind of picture gives not a very positive view of this answer, because it seems to be very difficult. This is both mesoscopic, you have long range effect of microscopic configuration, and it's also very non-isotropic. It reveals the structure, the within structure of your...
If you had more disorder in the sizes of the particles, then you would destroy those lines, right?
Yeah, you destroy these lines, but you keep... Yeah, you destroy it. I can show you another picture where it's less structured, but you still have smaller lines, and then a complicated network of such lines. Just an example of something that is in the internet, which I discovered a few years ago. It's in San Fermin in Spain, and you will see they will get to a space, a corridor with a very large door, and you will see they are motivated to run. You understand why? And so there is no... it's nice. Here you have that. So you see, it's not very clear what happens, but you will really have some kind of a jam, and people are pulling, and it seemed that it's a bit like...
the others from getting out, or
they... What do you mean? No, they try to... There are some people at the end, my guess is that they are blocked, completely jammed with other people. And some people here, they try to pull, but it's impossible because it's very stable, actually. And the more people push, the more it's stable, actually. And so it's a bit like that, even if it's not a scientific experiment, I think it's... And this is a nice... So this is not crowd motion, but perhaps it addresses a bit your question. This is a granular flow. It was performed with Sylvain, who you saw yesterday. It's a ball, a tracted ball on a bed of very small particles, grains. And it's slightly I don't remember exactly, perhaps 20% plus and minus the polydispersity. And you have 300,000 of grains. It corresponds to an experiment that was made at FAST here at Orsay. And you pull the white one, and this is what you get. And what is represented is is the forces, the pressures. So you see, I don't know if it's very clear. Yeah. So you see it's very irregular in time, of course. So there is no continuity in time. And it's also very irregular in space. It seems to be difficult to imagine a macroscopic model that would describe this set of constraints. And that, of course, the structure is moving. It strongly depends on the structure itself. It's very long range. You have long range effects.
It's very strange how much you have on this side.
Yeah, but yeah, that's right. It's probably close to. Yeah, it's very far. It goes. It's highly dense, so you have propagation of those contact forces, and.
This is a hard boundary here on this side?
This is a hard boundary. Let me. I don't remember if it's if I took the if we see the boundary. No. Yeah, yeah. Perhaps there is a. I should have. Sorry. Yeah, perhaps this is clearer. Here you have typically over there you have a hard boundary, but here you have a quiet zone. But I guess it advances like the velocity of the ball. But here it's not exactly highly packed. Here it's highly packed, and the ball it pushes, so it becomes highly packed, and then things can propagate to the network. Okay. I told you yesterday about this beta I procedure to improve things, to put some social behavior. That's as I told you at the beginning, my talk was not oriented to find psychological behavior of human being. This is the only slide that will talk about that. You can consider the gradient flow, but you put some beta I, that is an individual weight. If I am I, my beta I is between 0 and 1, and it corresponds to the weight I put on my dissatisfaction on the global dissatisfaction. So if I am very angry, I want very selfish, I will have a strong beta I. And if I say, okay, if it's not, let me forget about myself, I will have my beta I go down. And what we tried to model, it was actually, we didn't know where we were going, but we do this model. We start from the jam that we had 2 slides ago, like the fully blocked jams. And then we turn on this model. It means that when someone is stuck, the guy would like to advance, but it cannot, and there is someone in front. And then the beta I is reduced. I decide to reduce my beta I to say, okay, just stop pushing. There's no worse. It's no interest in pushing, so I do not stop. I don't know that it happens in practice, but be clear, you are being civilized. See, you cannot, you are not pushing like an animal. And that is what happened. This is the jam at the beginning, and at some time you will see that almost all people stop pushing, and immediately you have a fluidization of the crowd close to the door, because what was stabilizing the jam was precisely the people upstream continuing to push, even slightly, but a lot of them, so it creates strong forces, and you find that so it's something that is known in crowd motion modeling. Slower is faster, in fact, or usually they say faster is slower. I talked about that. Is people try to rush, and usually it decreases the speed actually. So this is the reverse. If you just slow down, it will go faster. But of course, as I often say, it's difficult. Is it realistic? I don't know, because this one, for example, he has been waiting for a few hours. So you might imagine he can get a bit excited in reality.
But so what is the process and the beta I's here? Do they?
Oh, it's not very elegant from mathematical standpoint. Just for each particles, there is some kind of a test. You say, if we estimate some kind of frustration. I want to go in this direction. My actual velocity is less in this, so my frustration goes up. So I am frustrated. And if I am frustrated, I have my beta I go down. I lower progressively my beta I up to 0. And that's why people that are here, they would like to go there, but they cannot, so they just stop pushing. because what is represented here, the black is the desired velocities, not the actual velocity. So it gives the idea of forces. And as soon as people advance, then it gives me some space to advance. So it's some kind of civic or civilized behavior. Okay, and this is actually it suggests that this is a local minimizer. This is the global dissatisfaction represented here. And the frustration here, it increases for some people. And what is important, the dissatisfaction. Here, when people go smoothly, evacuate, then the dissatisfaction is reduced. You are in the steepest descent, you decrease your dissatisfaction. Here you are blocked. And then you, with this beta I, actually, is like if you accept to increase your global dissatisfaction, and then you find another path to go down. And that's what happens in practice with this evolution in many phases. It can actually be checked. There are some experiments performed in Spain. They have been performed also with sheep. But because they are good animals, there is no problem, no security problem. They are well protected. And for people, it's a bit more complicated. It's difficult to organize that kind of things because on the right, they ask, okay, be really pushy, and you see that they almost straggle each other. And it can be shown that though they try to go faster, and they actually go more slowly. And it's the same for the computation.
Sorry, Bertrand, have there been experiments where they like so you pick half of the individuals to be aggressive and half passive?
Numerical experiment, yes. That's actually a question I asked myself. This is my intuition, is that the optimal way should be a mixture between both. But concerning I think there are some papers on that, but I don't remember that there are very significant results. But I would expect something like, well, like I said, I think in the first lecture, that might be, because if you have very aggressive people, it clearly doesn't work. Too polite people, they are just a bit shy, and it does not work so well. But you have some bullies and shy people, it goes very fast actually for the bullies. And after you have the shy that follow.
So what kind of philosophy is that? You should be a bully.
yeah. But if, well, I don't know.
Assuming that not everybody is.
Exactly. So this kind of game theoretic position. Okay, I think there is some experimental also. Is something there have been some experiment with little unpronounceable animals like Chlamydomonas rendarti. We worked with people, physicists in Grenoble, and what is very surprising, because in that case there is no real contact. They are in a viscous fluid like Stokes fluid, zero numbers, and we observed faster is slower effect. We can control the speed of the swim, and actually there is a faster is slower effect, which is very puzzling actually. I just want to show that this kind of problem can be met in other contexts than crowd motion, but I have to say that I'm not a full explanation of for crowd. I see that I have a start of an explanation, but for that no. But I think you
I had a question. Is there experiments in biology where you see that the individuals in the crowd learn that they should go slower, or be less pushy? Or?
Yeah, that's a good question. That's a very good question. It's perhaps that what you observe in practice, if some population survives, is probably that they learn that they should not be too pushy. But to have an experiment on a scale such that you observe the evolution genetic, I have no. That's an interesting question. Perhaps in the real biological world, that might be difficult to have to wait for things to evolve. But it's something that is an important question in biology. I know they have in some cells they have cheaters, and also I don't know the other ones, and that's why there is some complex questions about game theory, theoretical modeling of what happens in terms of selection. But I haven't seen that for crowd motion, for things like that. But that's an interesting point. Well, just some example of the macroscopic motion. Actually, it's too smooth. It's like a fluid. It's not very interesting and realistic. So I just show that. I'm not going to detail how we do this computation, but the algorithm, it's stochastic actually. It's very difficult to compute in another way. It's based on some kind of Brownian motion that mimics the Laplace operator that is here. And I think that's basically it. Perhaps I will finish with an obstacle thing. Huh?
3 minutes.
Yeah, I'm stopping here. This is an example, another paradoxical effect that you can observe that is very difficult to reproduce, but sometimes it happens is because of this non-convexity, this bizarre Laplacian, by adding an obstacle, you might improve the evacuation. But don't try to do that, please, or don't say it came from me, because it will not work in any situation, in all situations. But here, it's some case, it's you in some way you canalize things. You break the jams, but it doesn't work always. So don't do it. And that's it. Thank you.
Other questions? Yes.
On that animation with the large crowd and the one larger ball pushing through, and there's these propagating forces.
Yeah.
It seemed like there was kind of a hard boundary, some radius from that sphere that was pushing through. Some maximum distance that you were seeing the forces propagate to. Do you have any explanation for
Yeah, actually, it's a bit our fault because it was not in the experiment. The problem is that it's very, very difficult to produce random, maximally packed situation. Basically, you put particles and then you squish them and then you push but when you do that, usually it's not perfect. So what happens is that, and if it's not really highly packed, nothing propagates to the pressure, the contact pressure, because if there are some holes in the contact network, it cuts the propagation. So what happens is that we have at first we have something that is almost packed, but the ball itself, it pushes and then it becomes really packed, and then this thing can propagate. So what happens is that if you are too far away, you have not yet realized this compactification, so that you have something that is quite dense, but not dense enough so that things can propagate to the network simply, but there are slight holes, you have intergaps between particles. You see?
Yeah. That doesn't seem too surprising for an actual physical, setting where the propagation would have limited.
Yeah, sure. But actually, in the experiment, they probably have special protocols to make dense situation, and it went farther away. They are able to produce really highly packed situation in 1D better than we can.
Other questions?
So,
So in the simulation you showed of the exit from a building, which was a little complicated when you talked about architects and so on. There was and so you had the isocline for the distance. It was surprising because in the end, I'm asking generally, how can one even predict who would be the last to get out?
That's
and here you had a region which was not that far, and they got out much after everybody else.
Yeah, that's a good question. Sometimes actually we put colors on people depending on their position, initial position, and then we see that it's not at all respected. Yeah, and it's depends on the configuration in a complicated way. Even for a simple jam, you can have, for example, we saw in the polite situation, you have people in the center that go much quicker. So you have people that were close to the door that exit almost at the end. And of course, it's much more complicated with when you have a complicated building. Yeah, that's a right point. There is no justice in that. You might have people that were close to the exit that go.
But in your simulation, we also saw that this region was at some point became very, very packed.
Okay, yeah, I told you we exaggerated a bit just to have some nice pictures.
Maybe related to the previous question, I was wondering if you can measure avalanches and things like that. So when you push on the big particle pushes on the medium, then you have these different lengths and then strengths, and they move, and so can you measure and describe a bit the structure, how it spreads? And
I have not been working a lot on this direction. Actually, Sylvain interacted with physicists at FAST. I know what they built some kind of equivalent stress tensor. The first, we have only pressures between particles, but you can, for each particle, you can build some kind of a tensor, well, 2D here, because it's 2D, that plays the role of a stress tensor. So you have some kind of macroscopic ingredients, some of these tensors, that of course depends, highly depends, is very irregular. And that's what they do, and they try to estimate also how far it goes, a bit like the talk before yesterday that you have on mean field games.
Yes.
Cecile, sorry. You have those, you estimate the amplitude at which distance you have an action of what you. Yeah, there's something that can be done and in practice in the experiment and also in that. But I'm afraid I'm not a real specialist. I participate in the computation and the numerics, but I didn't explore that in detail.
I think we should stop here because we need enough time for lunch. And so thank you very much.
Thank you.